Hi, welcome back to AP Physics 1, Unit 2. This is our dynamics unit. Excuse me. So in the last video, we talked about Newton's first law. Now let's continue talking about Newton's laws of motion. And so we're going to focus on Newton's second law. So previously in the first law, we were talking about balanced forces. So here in Newton's second law, we're going to talk about what happens when those forces become unbalanced. So what happens is when you have these forces acting on the object, the net force will now no longer be zero. Okay, so what does that ultimately mean? Is that it brings us to Newton's second law. And so what happens is this is Newton's mathematical law. So it states that the acceleration of a system's center of mass has a magnitude proportional to the magnitude of the net force exerted on the system as in the same direction of that force. Okay, so mathematically what that means is that the sum of the forces that act on an object is m times a. So mass times acceleration. In fact, Newton didn't define it for force, he defined it for acceleration. So what he's saying is that the net force that's acting on an object is directly proportional to the amount of force exerted on the object, but inversely proportional to the mass of the object. So if I have a small mass, I would have a greater acceleration to produce the same force that if I had a big mass with a smaller acceleration. Okay. And then what happens is we talked about this in center of mass video. So the velocity of a system's center of mass will only change if a non-zero net external force exerted on the system. So in the center of mass, we talked about the velocity of the center of mass is sum of mi vi over the sum of mi. And what happens is for this to happen, you have to have a net force, or for that to change, you would have to have a net force acting on the object, which means then you would have to, that is what causes the change in this for the system. Now, what happens is most of the problems that we will encounter in this unit will be Newton's second law problems. So you have a couple over here. One common one is the incline plane. And then you also have what are called connected objects. So those connected objects problems tend to be a fair amount of, they may have some work to do with them. There'll be two blocks pushed together. There'll be Atwood machines where you have two masses hanging from a string and a pulley. There'll also be what are called modified Atwood machines, which is very similar to what you actually see in the incline plane picture, where you would have an object on a table, mass hanging off, then that mass causes the cart or whatever to accelerate up or on a surface, up the incline on a surface. But that is those are the types of questions you'll run into when we talk about dynamics, Newton's second law. So let's look at an example problem. So here is a derive an expression question. So what we're going to do is we're going to derive an expression for the acceleration of an object with mass m down an incline at angle theta, where the friction between the surface and the block is negligible. There's going to be a complete video later about friction. And so what happens so we're going to first derive the expression for the acceleration, and then we're going to talk about what happens to the acceleration if we increase the angle. And then we're going to justify our answer. All right, so in our problem solver process, first thing we do is draw a free body diagram. So all the forces that are acting on the object. The first force you always draw on here is an object's weight. Then the other force that would be acting is the normal force. Now, we don't necessarily have to worry so much about the normal force or the effects in the y direction, what amounts to it, because there's no friction involved, so we don't have to worry about the normal force. And so what we do, we always put our axis right in the direction of the precede motion, which would be down the incline, And then that allows us to break apart the FG into two components. So we would have FGY and FGX. In fact, the FGX is the only component that is pulling down this block. Now, through the magic geometry, the theta, the angle of incline, will equal the angle in our triangle there. And this is a case in which you would flip your x and y for your sine and cosine. So typically it's x goes to cosine, y goes to sine. But in this problem, or in inclined plane problems, you're going to flip it. So FGX would be mg sine theta, and FGY would be mg cosine theta. So we don't really have to worry about FGY in this problem because we don't have to worry about that normal force. But we would say that the net force in the x direction is equal to m times a, because we're accelerating down the incline. And the only force we have acting is mg sine theta. In fact, this is how easy this problem is, right? So that m cancels that m, and so the acceleration is simply g sine theta. So that is the acceleration down the incline. And then the question becomes, what happens when we increase theta? So what happens to the acceleration? So what you'll see, if we go from 0 degrees up, remember sine of 0 equals 0, right? And sine of 90 equals 1. So what happens is as we increase the angle, our acceleration is also increasing. And what's our justification? Because what is happening is we're going from like no acceleration here, right? And as we start bringing up that angle, we're going to our maximum values when the object would just fall straight down, right? So we're going from an acceleration of 0 to an acceleration of 9.8. And so our justification was like, as you increase the angle, the acceleration increases due to the sine of the angle, thus going from 0 degrees to 90 degrees, going from a value of 0 to a value of 1. Okay, so that's going to end our talk about Newton's second law. One thing to remember, a lot of the questions that you will encounter from here on out will have a second law focus.